Okay, so that's kind of a generic potential. Now I want to do gravity for realsies. So we had that the gravitational potential, we had that in general, the derivative of the potential with respect to some direction is minus the force. And the force of gravity is like that and radially inward, gmm over r squared. So I'm looking for a u sub g such that if I take its derivative, I'm going to get gmm over r squared. Oops, I didn't say that right. I take its derivative with respect to r, not g, not m, the little one. Okay, so what would that function be? Any candidates? I see the yawn. He says, everybody knows. Okay, fine. So what do you propose? U sub g is equal to? I have to be able to take a derivative and get r squared on the bottom. So I think I need r on the bottom. R, yeah, fine. Okay, so I have r on the bottom. What about a minus sign? Do I need that? Yeah, okay. Duh, of course. All right, so if I take the derivative of that, I would get gmm over r squared. But there's a question. Erkingley. Where's the zero of gravitational potential energy? Just go there. Just kidding. Just kidding, all right? Yeah, infinitely far away. So we're going to treat gravitational potential energy. If I do that for uniform gravity, it doesn't really matter. It only cares about the changes in position. It's true that this one only cares about the changes of position, but the only cute position I can stuff in there is infinity for r to define the zero. So that's what we do. We define the zero. That means it's never positive. Is that right? It's always negative because r has to be positive and allowed to be between 0 and infinity. Okay? So what would be the escape velocity from the Earth? So in order for something to escape, and this something apparently is a very tall rocket, or the Washington Monument, I'm not sure which. So it's going to blast off, and we will say that we can neglect the time over which it's accelerated up to some speed v naught, and then it just coasts. It just goes on its merry way, but gravity keeps tugging on it and pulling it back. And the question is, how fast does v naught have to be for it just to leave and get out of the Earth's gravitational potential well? So initially it has kinetic energy like that, and gravitational potential energy of minus g m over the radius of the Earth. Is energy conserved as it coasts? Okay, so we have to ask, are there any non-conservative forces on it as it's flying away? Friction. So we're going to assume that we're outside the atmosphere and we can neglect friction. And that's the same. So we're going to neglect Mars, yeah. No candy bars. All right, so this will be equal to K final plus U final, statement of energy conservation. What's K final at minimum? 0. And what's U final? Aha. So therefore, V naught, 1/2 m V naught squared is equal to big G, big M, little m over radius of the Earth. So therefore, V naught is equal to the square root of 2G big M over the radius of the Earth. So if we have that much initial speed, anyone have a guess as to how big that works out to be? Over 9,000 somethings. Yeah, right. Okay. So I'm going to use a nice way to estimate, because I happen to remember that little g is 10, roughly, meters per second squared. So this looks a lot like little g, except for what problem? Yeah, okay. The acceleration due to gravity is the force of gravity divided by the mass of the thing. And so that would be big G, big M over R squared. So this is the same thing as the square root of 2G wrong. 2G R sub E. No line. Cut that out. Okay, do we agree with that? Because little g is equal to big G, big M over the radius of the Earth squared. So if I multiply that by radius of the Earth, I'm good. So I can calculate V naught. I'll put an approximate because I'm going to be real sloppy here. Square root of 10 meters per second squared. What's the radius of the Earth? Exactly. 6.4 times 10 to the 6 meters. Can't be done. Ah, yes, it can. Okay, so if I multiply here, then I have a 2 times a 64 times 10 to the 6. And I got the right units. So that's an 8. That's 1,000 times a root 2. Root 2 is 1.4. So this is 1.1 times 10 to the 4 meters per second. So a bit better than 10 kilometers per second, which is fast, but not on the scale of c.